Well, welcome back. I trust you had a good break. Audrey had an eventful break, and so we won't be calling on Audrey much today, as her mouth is somewhat swollen and in some pain, though not as bad. You said this morning, and it didn't actually sound that bad. I'll still try not to call on Audrey too much, and she's still here. She's here. It's not like Kendall where she was gone. She's here. It's good to have Kendall with us and Michael with us. Go ahead and turn your textbooks, if you would, to page 186. Page 186, and we're going to finish up our study of mechanics. We've been in mechanics for all of the second quarter, the last part of the first quarter, and here the first part of the third quarter, so a lot of time spent here, moving a little slower than the curriculum calls for. So if you were taking an Abeka video class, they'd be already done with mechanics by now. I wanted to spend a little bit of extra time, make sure you had a good understanding of it. And this next chapter is our last chapter in our study, and what we've been dealing with had been primarily translational motion. Remember, if you go back in your brains, a long time ago, translational motion results in a change of position, so movement from here to here. We also looked at something called periodic or oscillatory motion, right, where the object moves from here to here, but then it goes back and forth, right? So the object, it does change its position, it just goes back to its original position over and over again in oscillatory or vibratory motion. The last type of motion we need to look at, first thing in your notes here as we start a new chapter, is what's called angular motion. The root word that you see here is angle. And with angular motion, the root word of angle, remember, an angle simply refers to some rotation that occurs. Technically, there's two aspects to angular motion. The first is something we have looked at already, and it's circular motion. Circular motion is a type of angular motion. It's not going to be our focus in this chapter, but I did want to reference it. Technically, there's an angular motion there. Circular motion, though, here's the key word for circular. Circular motion equals orbit. For instance, the Earth goes around the sun, not in a circular pattern, but it's kind of close-ish, as we talked about, right? So that's kind of like circular motion. A yo-yo going around your finger, that's circular motion, because the yo-yo is orbiting your finger. The moon going around the Earth, it's orbiting roughly in a circular pattern, right? It's orbiting, and the key is it's going around what we would say is an external axis. Your finger is not part of the yo-yo. The sun is not part of the Earth. The Earth is not part of the moon. So when an object is in circular motion, that's a type of angular motion in which the object will orbit an external axis. That's not what we're dealing with in this chapter. We're dealing with the second aspect of angular motion called rotary motion. And that's what we're going to focus on here in this chapter. Rotary motion is an object that is spinning. That's the key word to think of. The object is spinning on what we've described as being an internal axis. The object is spinning on what we would call an internal axis. For instance, we know not only does the sun go around, or the Earth go around the sun, could get a little Ptolemy there. Anyway, not only does the Earth go around the sun, but while it's going around the sun, the Earth is also spinning on its own internal axis. Now, again, the axis isn't a physical object that pokes out at the north and south poles, right? We understand that, right? Unlike, the Santa Claus. It's the North Pole coming up out. No, there is no such thing. Anyone watch that movie this Christmas break? We watched it last Christmas. We kind of alternate years so we don't get bored with Christmas movies. But anyway, there isn't an actual physical axis, but there is, right? There's not an actual axis on you, but for instance, if I'm spinning, this would be rotary motion, okay? The object is spinning about a point within it, or an axis of a sense within it, and that's the idea of rotary motion. That's what we're going to be looking at. So again, you understand then why we would call it angular motion as well, because as I face this way, if I spin, I have turned a certain angle. Does that make sense? So as I've turned a certain angle, I have spinned, and moved that way. Anyway, with this angle then, I'm going to take you back, Kendall, to your geometry days. Now, this is not something he's learned yet. Okay, he's going to get it very, very soon. In fact, my bulletin board is all about angles in circles. You might remember that. Angles, we have inscribed angles, angles formed by intersecting chords, all that cool stuff. But the easiest of all of them, Kendall, you might remember, was that in a circle, if you had an angle formed by two radii, Michael, you would remember this because we have talked about this, an angle formed by two radii is called a Uh-oh, Christmas break got him. Central angle. A central angle. We'll represent it in this class with the Greek letter theta to indicate an angle. That's what we've used before. And we said this, that whatever the measure of the intercepted arc was, in degrees, for instance, we would say this is maybe a 52 degree arc. Well, that's because this is a 52 degree angle. So there are angular degrees and there are arc degrees. And in geometry class, we always measured arcs in terms of degrees. So if you were to take all the arcs of any circle and put them together, we would say there were how many arc degrees in a circle class? 360, because there's a full paragon, or 360 degrees at the center of the circle as well, right? Sum of all the angles about a point is equal to a paragon of 360 degrees. So 360 degrees in this arc here as well. The problem is that's not super intuitive, right? I even mentioned this when I was teaching it in geometry. I said, the hard part is we're used to thinking of this as how many inches long, right? And in geometry, we couldn't go there. We had to settle with how many degrees is the arc, and again, it was based on its central angle. Well, if that's true, we could make a proportion, Kendall. We could say that arc is to the whole distance around the circle. Anyone remember what we call the distance around the circle? Hey, very good, circumference. Okay, so the arc is to the circumference as the central angle is to 360 degrees, right? The only problem with this is if you were to cross multiply here, right, you'd end up with all extra degrees, and you don't want degrees for the arc. We don't want degrees here. So what we would need to do is we need to find a replacement for 360 degrees. We need to find another way to define the paragon. And so what mathematicians did to come up with a unitless angle measure is they said, well, let me increase the size of the angle ever so slightly. If I were to take the length of a radius and I were to curve that length of the radius over an arc so that this arc is equal in length to the radii if it were flattened out, we're going to call this particular angle 1 radian. Radian like or pertaining to the radius. So the angle that makes an arc equal to the radius is called a radian. It's about 57.3 degrees-ish, plus or minus-ish. Well, you might also remember, Kendall, we had this construction. I didn't bring my compass with me here, but if I took my compass and I made a circle, you might remember I said pick any point on the circle and take the compass, open that same length, mark off an arc, 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 mark off an arc. They would go all the way around. Why? Well, because what you'd end up forming then is a chord equal to the radii. You'd form an equilateral triangle that way, which means you have a perfect 60. And then another 60, 60, 60, 60, and there's your 360 degrees. But here you see that the chord is equal to the radius. Shortest distance between 2 points is a straight line. So this straight line, if it equals the radius, then the arc, which is not a straight line, must be longer. It must be slightly longer than the radius, right? So we would need to shrink that angle down to, like I said, about 57.3 degrees, so that now not the chord, but the arc equals the radius. Well, what that means, Kendall, is instead of 6 of these, you need a tiny bit more than 6 of those, right? If you took 6 of this measurement, you'd end up getting to right about here and you'd be done, right? You'd have used up your 6. We actually need about 6.28 of these radians to go all the way around a circle. 6.28. They know what I mean. I'm curious if you know. Do you remember what 6.28 is? It's a special number we used in junior high. Remember pi is 3.14? That's 2 pi. And so there are exactly 2 pi radians in what's called a revolution. One complete paragon has exactly 2 pi radians in it. So what we can do then, Kendall, is instead of using 360 degrees, arc is to circumference as angle is to complete revolution, we could take the angle in radians and then compare it to 2 pi, because technically radians are unitless. It's just a number of whatever, right? Arc then is to circumference. Anyone remember how we find the circumference of a circle going back to our junior high days? C equals 2 pi r. So we could replace the circumference with the formula used to find it, 2 pi times the length of the radius. Arc is to 2 pi r as angle is to 2 pi. Well, if there's a 2 pi in both denominators, they cancel, which means that the length of the arc is to the radius as the central angle is in radians. Or, if we're to cross multiply arc times 1, we could say that the arc length equals the length of the radius times the central angle, but measured in radians, not degrees. And if you look at your calculator, Kendall, across the top, you see a button that says DRG. If you push the button, you'll notice that at the very top of your screen, there's a little word that changes. It goes from saying deg to rad, right? And so that goes from degree mode to radian mode. So the angle in radians times length of radius equals the length of the arc. To put this then in a formula, we just need a good letter to represent arc length. Arc length. Well, naturally, we would choose the letter S. All right? I think S for sector of a circle, because the arc defines the length and size of a sector, but whatever. S equals R theta rad. This is the first formula for you to get in your notes for this chapter. S equals R theta rad, where S is the arc length. By the way, we have another name for the arc length. Imagine a merry-go-round. You rode a merry-go-round when you were little, right? And imagine the merry-go-round, and you go around in circles, right? There is a certain angle that the whole unit is displacing. If it only turns a little bit, there's a certain angle that you have turned along with the merry-go-round, but you have physically traveled from a certain point to another point, correct? Not in a straight line, but still you've traveled from one point to another point. So arc length is a form of displacement as well. Now, technically, it should be called the curvilinear displacement, but we're lazy. But we are going to refer to it as the linear displacement. Displacement. So the arc length will sometimes be referred to as the linear displacement. Equals R, of course, we know that's the radius. We've seen that letter often enough. And then the theta rad, of course, is the central angle of rotation. It is sometimes referred to as the angular displacement. The central angle of rotation is sometimes called the angular displacement. Now keep in mind that 2 pi radians is a revolution. Or we could say that 2 pi radians is 360 degrees. If that's true, if you divide both sides by 2, it means that pi is equal to 180 degrees. Pi radians is the same as 180 degrees. So one full 180 is a rotation of pi. In that case, thinking dimensional analysis, remember we said dimensional analysis multiplied by a series of fractions until you get the unit you want. So if I had feet and I wanted miles, right, I would multiply by 1 mile over 5,280 feet. If I had seconds and I wanted hours, I would put the 1 hour over 3,600 seconds. If I had meters and I wanted feet, right, I would put the 3.281 feet over the meter, right? If that's true, then we can use the equivalence between pi and 180 degrees to convert back and forth between some different units. So let me go ahead and get these conversions down for you. If you happen to have degrees and you want radians, this is normally how things will go in this class. You have degrees and you want radians, because we can't use degrees. This has to be in radians. If we want have degrees, want radians, we're going to multiply by pi over 180 degrees. And that'll get rid of the degrees. By the way, let me just clarify. This rad is a sub-notation. I almost wrote it like it's next to. It is a sub-notation. Just to specify, as a reminder to you, you must use radians for your angle, not degrees. However, there are times, right, we think in terms of degrees, right? If I said I want an angle of 2, right about there would be 2 radians. We don't think like that. We think of that as being, somewhere around 120 degrees-ish, right? We think in degrees. So for our own reference, it may be needful for us to take radians and convert them back into degrees. Well, in that case, you just multiply by the reciprocal, 180 over pi. 180 degrees over pi. If you have radians, and for some reason you want degrees, just because that's an easier way to think. Another big one, though, will be revolutions. A lot of times as things spin, real life, things don't partial spin very often. Right? Especially a lot of the things that we would be looking at, like a CD spinning in a, you have CDs still? DVD and DVD player? Okay, it spins, right? It's not spinning a partial spin. It's spinning bajillions of times in a little bit of time, right? It spins really, really fast. So oftentimes we'll have revolutions, meaning complete spins, and we will want to convert that into radians. Well, if you remember that a complete spin takes 2 pi, all you have to do is multiply by 2 pi, and you've got the radians. So 3 conversions that we'll need to know and be able to use in this chapter. Now, if you feel a little bit lost, Kendall, and if you're watching, you say, I'm still a little fuzzy on the radian stuff, okay? We're going to do a little bit of practice now. If you feel lost, I'm going to put a link in the description. Kendall, lesson 16 on my pre-calculus playlist. Lesson 16 has a much longer introduction to radians, a lot more practical practice with it. You'd want to start at the 12:47 mark, the 12-minute 47-second mark. We'll give you some more practice with that. For now, though, turn to page 188. Turn to page 188. And let's take a look at the example problem. Take a look at the example problem here. It says perform the following conversions. 1 degree to radians. Get your calculators out if they are not already. Now, you don't actually need to be in radian or degree mode for this because we're not really plugging in any angles. The degree or radian mode on a calculator is for if you're plugging in an angle. We're not doing that here. But if we wanted to have 1 degree and convert it into radians class, we need to multiply by pi over 180. So we're going to take our 1 degree, we're going to multiply it by pi over 180 degrees. Now notice the degrees will cancel each other. What units do we have left? Nothing. Radians are unitless. Okay, so might be something to jot down, by the way, in your notes, that radians are unitless. So there's just 1 times pi, 1 times pi, or just hit pi, and divide by 180. And what is a degree in terms of radians? 0.0174, blah, blah, blah. Did it do 1.0 degrees? It did. So they want 2 sig figs. So we say 0.017 to get our 2 sig figs in there. A very small amount of a radian. Then it says convert 35 degrees, to revolutions. 35 degrees to revolutions. Well, if I want revolutions, I would need to use the dimensional analysis to say that a revolution is how many degrees, class? 360, right? The 2 pi is a new concept. I didn't write this up here. I suppose if you wanted to write this down, degrees to revolutions, you divide by whatever. We know that a revolution is 360 degrees. So put the revolution over 360 degrees. Notice again, the degrees are going to cancel. Now here we do have a unit. It's revolutions. How many revolutions, or what fraction of a revolution, I should say, is 35 degrees? .0972 repeating, or roughly 2 sig figs again? No, 3 sig figs. Well, let us say 0.0972 revolutions. Okay? It's a small part of a revolution, right? 360 degrees is a full revolution. More than that's more than a revolution. It's just about a tenth of a revolution. 36 degrees would be exactly a tenth. That's getting close. Questions on that? Look at the next one. It says convert 1.5 pi radians into degrees. Now notice they have 1.5 pi rad. Note that notation, RAD. Kendall, they will often use rad just because we're so used to having units. It's weird to have no units, right? AMA, IMA, those were kind of ratios, so we kind of understood those not having units, but we're so used to having units. If you put rad for a unit, for instance here, if you said 0.017 radians, I'll let you put the rad as a unit, no problem with that. The book often does that, not because it is a unit, just because we're so used to having units. But if we want to convert 1.5 pi radians into degrees, to go from radians to degrees, class, there we go, multiply by 180 degrees over pi. Now in this case, Kendall, since they used pi in the original, it can cancel with that pi. So rather than multiplying it all and then dividing the pi, cancel the pi out, it's just really 1.5 times 180 degrees. Which comes out evenly, class, to 270 degrees. Now, you two in pre-cal think of 3 pi over 2. Oh, 3 pi over 2, of course that's 270. We have that one memorized. But 270 degrees is 1.5 pi's. Look at the last one here, 2.7 revolutions. Well, again, a revolution is how many radians? 2 pi. A revolution, a complete turn, is how many degrees? How many radians? 2 pi. So all we have to do is multiply that by 2 pi. Technically, you say 2 pi radians over 1 revolution, and so the revolutions cancel. And so we take the 2.7 times 2 times pi. And how many radians are there in 2.7 revolutions? There we go. Or we could round off. It's 3 sig figs again, right? Yeah, to get 17. And again, we could either leave it unitless, or if we said rad for radians, that would be fine as well. Questions on these conversion factors? Again, you've got to know that a complete turn, a complete spin all the way around, a revolution, has, class, how many degrees? 360. How many radians? 2 pi. If you remember that much, you'll be fine mostly. Again, more practice on that in pre-calculus lesson 16. Link in the description of the video. So then, there are some different values that we've used as we've talked through mechanics. Different things we've talked about for things like velocity and displacement and acceleration and time and initial and final velocity and average velocity, all these different quantities that we've talked about, right, in terms of movement, but it's always been in a straight line path. We can make analogous ideas to that if we were to go into the angular realm. So we have different quantities that are angular in nature for rotary motion. For instance, angular displacement doesn't mean that the object has moved any distance from point A to point B, but it does mean that an object has spun a particular angle. The bigger the angle, the greater displacement. For instance, if I turn from here to here, that's a little bit of angular displacement. If I turn from here to here, that's a greater angular displacement. If I turn from here to here, that's dizziness and a greater angular displacement, right? The bigger the angle is, the more rotation there is, and you can think about that. Amount of rotation, that's the angular displacement. Well, we say that amount of rotation is an angle, right? So literally angular displacement, that's going to be represented by the theta rad. Angular displacement is the theta rad, or the book will often just use theta. I use the theta rad to remind you it better be in radians. Well, keep in mind, we had the equation earlier, S equals R theta rad. Do you see that in your notes? I had to erase it off the chalkboard to make space, but you still see S equals R theta rad in your notes. What would you have if you got the theta rad by itself? You get S over R. So this is not technically a new equation, but still write in your notes as if it is. It's the same equation you wrote earlier, but now solve for the theta rad. Important to note, displacement, the distance from me to Kendall, the distance from me to Audrey, the distance from me to the door, especially if there were donuts at the door. Anyway, the distance from me to wherever, right? That straight line distance, we would measure meters. For an amount of spin, we don't measure it in meters. It's an angle, and we measure angles in radians. No longer degrees, but radians. Or leave them unitless. That's angular displacement. Well, keeping in mind that angular displacement could be represented theta rad, let's talk about this. An object, for instance, could spin at different speeds. For instance, any of you ever seen a record player? Okay? Now, those spin, but they don't spin super fast. Not like a CD player. Right? They both spin, but they spin at different rates of speed, correct? Because one is using a needle to detect grooves, right? The other is using laser technology to read imprints, right, on the disc. So they spin at different rates of speed, right? Now, speed, we don't really use that term. We normally use the term velocity, right? Velocity meaning the rate of speed or displacement per unit time. Well, for spin rate, we could do the same thing, but we would call it angular velocity. Angular velocity. And in parentheses underneath that, you could put spin rate. How fast is it spinning? Well, remember, for regular velocity, v equals d over t, right? Velocity is displacement per unit time. So angular velocity is going to be angular displacement, or theta rad over t. Just angular displacement per unit time, the angle of spin divided by time. But we can't use v for velocity because it's not the same thing. V is referring to a straight line velocity, if you will, an actual displacement from one place to another. So instead, we're going to use the Greek letter omega. It kind of looks like a W. That's the Greek letter omega, where an actual W would come to a point at the bottom. It's more rounded and kind of curls in at the top if you're trying to form an omega well. But the Greek letter omega equals theta rad over t. Remembering that theta rad is essentially radians per second, it makes sense then that omega, or angular velocity, would be radians per second. Or just per second. However, we don't typically use hertz. Hertz is technically oscillations per second as well. We don't use hertz for spin rate typically. Well, consider this. The wheels on the bus go round and round, right? I have small children, I know these things. All right, anyway, the wheels on the bus go round and round. And they can spin faster, they can spin slow. Now, of course, we're going to get into this later, but as they spin faster or slower, the bus goes faster or slower, right? Unless, of course, it's stuck in the mud and the wheels are just spinning. Hopefully that doesn't happen. But wheels can spin at different rates. The wheels could be spinning very fast and then they gradually slow down. For instance, you ever opened a CD player before the CD was done? So you got a chance to watch it spin or finish its spin rate, and it slowed way down, right? Or if you're spinning, you know what a top is, a little thing you spin on the table, watch it spin around for a while. Okay, so you spin that at a different rate, right? It starts out still, you kind of spin it and give it a nice speed, and then gradually slows down. Okay, something can accelerate or decelerate in spin rate as well. Well, again, that's not speeding up this way in a change resulting in a change of location, just spinning up the spin rate, speeding up the spin rate, or slowing it down. We call this angular acceleration. Angular acceleration. Remember, acceleration is always change in velocity per unit time. Well, if it's angular acceleration, it's going to be a change in angular velocity per unit time. So that we'll have not v sub f minus v sub I, but omega sub f minus omega sub I over t. Change in velocity per unit time. Again, it would be v sub f minus v sub I. That's what we had back in the, whatever was on the bulletin board way back when, right? But now it's omega sub f minus omega sub I because v has become omega. As we've talked about now, rotary motion is spinning. And instead of a for acceleration, we use the Greek equivalent alpha. Alpha equals omega sub f minus omega sub I over t. So instead of meters per second squared or feet per second squared, it's now going to be radians per second squared. Radians per second, which gives us radians per second squared. So some equivalences then to note. D has become theta rad. V has been replaced with omega. A has been replaced with alpha. As we go from the linear motion, motion along a line, to now rotary motion, motion resulting in a spin, we're going to change the variables, but the equations haven't changed really. Again, this is v equals d over t. That's an old equation. We've had that in a while. We're just substituting some different letters. We've had a equals v sub f minus v sub I over t. It's not a new equation. We just replaced some of the letters in the equation to reflect rotary motion. Does that make sense? Let's look at some of the math then. You're still on page 188, I believe. Look at example 13.2 and read that if you would for us, Michael.
A merry-go-round turns at a constant speed of 8 revolutions per minute for 5 minutes. Find the total angular displacement in radians and find the angular velocity, and the radians per second.
All right. So just like we did before, one of the things that I like to do is to write down all the numbers that I'm given. The first number we have, Michael, is
8 revolutions per minute.
8 revolutions per minute. Now, revolutions is an amount of displacement, isn't it? Angular displacement, it's an amount of displacement. Minutes is an amount of time. Any type of displacement over time is a measure of speed or velocity. How fast is it going, right? So 8 revolutions per minute, this is speed. But we said speed needs to be radians per second, right? So my omega is 8 revolutions per 1 minute. But I don't want revolutions per minute, even though it's a common unit we use in the US. I need radians per second for science. So I'm going to multiply some dimensional analysis here. How could I change either minutes to seconds or revolutions to radians? Kendall?
60 seconds in a minute.
There we go. Let's take the one we've known for a while, right? No problem there. Who goes where in the dimensional analysis?
The 1 minute over 60 seconds.
Good, put the minute over 60 seconds, and just like that, we have revolutions per second instead of revolutions per minute. I'm halfway there. I have the seconds. I want the radians. Class, how many radians are in one complete revolution? 2 pi. So how would I then form a ratio here, a conversion factor, to go from revolutions to radians, Michael?
Do 2 pi in the top and revolution.
Good. Put the 2 pi radians. Which radians are unitless? We don't have to write radians. If you do choose to write rad right there, that's fine as well, but we cancel away the revolutions. And so to find my angular velocity, 8 times 2 pi divided by 60. Or on my calculator, 8 times 2 times pi divided by 60. How fast? Now think about it, 8 revolutions per minute. I mean, think about this. This is a revolution. That's 1. If I only did 8 of those in a minute, is that spinning very fast? No. Fast enough to make me dizzy if I did 8 of them, but not really spinning that fast if it takes a full minute to only do 8. We shouldn't expect a very high rate of speed here, and we don't get a very high rate of speed. What is the angular velocity, Kendall?
0.8377.
And I believe it was 3 sig figs, because they said 8.00 revolutions per minute. Yes. So we could say 0.838 radians per second. Now, store this in the memory of the calculator, because we may need that. So I'm going to store that in memory 1. But there's my angular velocity in terms that I can use. I can't use revolutions per minute. You'll be given this a lot, by the way. So this process of converting minutes to seconds, radians to revolutions, you're going to do this a lot because this is, again, here in the US, this is how we define spin rate, revolutions per minute. So converting to radians per second, a valuable tool. And technically that was part B. Part A, find the total angular displacement in radians. Find the angular displacement in radians. Well, there's 2 ways to find angular displacement. One way would be to take the arc length divided by the radius. But do they tell me the radius of the merry-go-round? Do they tell me the total arc length traversed? No. They don't really tell me any of that. What they do tell me, though, is 5 minutes is the length of time. So if I have time, and I now have omega, I can multiply omega t to get theta rad, can't I? Right, just like if we said v equals d over t, we would multiply the velocity times time to get the distance. We did this all the time when we broke projectiles into x and y's. Except, my angular velocity that's in the memory of the calculator has been converted to radians per second. This is in minutes. Well, 60 seconds to a minute. How many seconds in 5 minutes, class? 300. Michael's like, I just came off Christmas break. I cannot do 5 times 60 yet. Give me a few more hours. 5 times 60, 300 seconds. Well, if you just take 300 seconds, then multiply it by what's on your calculator, you've got the first answer. And how many radians is the total angular displacement?
2.
Or round it off, we could say 250, yeah, you said 251. 251, we can leave it unitless like this, or you could say radians. 251 radians. Now, practically as well, think about it. Every minute, it makes how many revolutions? 8 of them, every single minute. So in 5 minutes, how many revolutions is that going to be? 8 revolutions every minute for 5 minutes. 40. That's going to be 40 revolutions, right? And every revolution is 2 pi. So another way we could have approached it, if we hadn't done this first, I did it first because I want to emphasize to you, always convert to radians per second. Because I said, well, 8 revolutions per minute for 5 minutes, that's 40 revolutions. What's a revolution? 2 pi. Could have done 40 times 2 pi. And you also get 251.3274. And that's why they listed as part A. Again, I want to emphasize to you that you're always going to want radians per second for your angular velocity moving forward. Questions on this example problem? Now, there are some equations we can extrapolate from this equivalency that I wrote out for you here. You remember on that bulletin board where we had those equations so long ago? There were 5 formulas. One of them was stupid easy. Average velocity is half of the initial and the final added together, assuming a uniform acceleration rate. We don't care about that one. One of them was v equals d over t, which we've already changed class to say omega equals theta rad over t. Another one's a equals v sub f minus v sub I over t, which we've already changed class to say right, so these 2 equations you already have in your notes. There was another one up there that said that the final velocity squared equals the square root of the initial velocity plus twice acceleration times displacement. Well, if we were to make an equivalency here, Kendall, let's see if you can do this. Instead of v sub f,
Omega sub f squared equals omega sub I squared plus 2 alpha theta rad.
is this a new equation? No, it just has a new look. It's like a new paint job. After she goes to the beauty parlor. All right, anyway, there's another equation that we had up on the board that was d equals v sub it plus 1/2 at squared, displacement for an accelerating object. Well, for rotary motion, Michael, I could change the way this looks.
Theta rad equals omega sub it plus 1/2 alpha t squared.
Notice time has not had to change, right? Time is scalar, right? It has magnitude. There's no direction to time. Time always presses forward. So 2 more equations for you to write in your notes. But again, I want to emphasize they're not new equations. Go and write them down if you haven't already. But they're not really new. They just look different. And we'll use them much the same way that we would have used the other equations. All right, now this is a shortened period today, so we did not get as far as I was hoping to get. We were supposed to practice with these formulas, and we did not have time. All right, so I'm going to shorten the homework just a little bit here. For homework this evening, I need you to read over pages 186 to 192. Read over pages 186 to 192, and read over what we talked about today. On page 203, answer questions 1 through 6. On page 203, answer questions 1 through 6. And on page 204, do problems 1 and 2. Page 203, questions 1 through 6. And on page 204, problems 1 and 2. All right, we'll take a look at all of this in our next lesson. Have a wonderful rest of your day, and you are dismissed.